And today we're going to look at his third law, which I like his third law just because of the wording of it. And his third law is all about, well, first again, I'm going to do a little recap. His first law, law of inertia they call it, is that if your net force is equal to 0, your object doesn't change speed, which means if it's at rest, it means it's not moving. It's not going to move. If it is moving, it's not going to change speeds. The second law is if your net force is not equal to 0, well, then F equals ma. Our third law says for every force, there is a reaction force equal in magnitude, but opposite in direction. All right, so an example of that, a couple of examples. The one I like is jetpacks. Jetpacks, more specifically in space, or even those water rides where the water hits the ground, or hits the water, I should say. I don't know if you've ever seen those things where people are spraying, where the water sprays down and then they shoot up and they can ride around the water. That's an example where the water is hitting, the shooting water is hitting the water and the water below is pushing it up. Office chairs, that's a big one. I always like to show that in class, using office chairs, where if you want to get somewhere, you push off and you go in the opposite direction. So often you push off your desk and to move backwards. All right, so our jetpacks in space often, as we just saw with the Mars rover, I'm not sure how many of you are science people that check that out, but the way they landed on Mars, because the gravity is different, that's something we are actually going to talk about this unit, but the jetpack shot towards the ground in order for the object to be pushed upwards. All right, so that is an example of Newton's law. We're going to look at it specifically. All right, so for example, here's a classic example of Newton's third law. Travis, who's 75 kilograms, is about to dock his canoe, which is 30 kilograms. He jumps off the canoe towards the dock with his foot, exerting a force of 155 newtons on the canoe. What is the magnitude of acceleration of Travis or of the canoe? Now, we're going to use two laws here. Again, Newton's laws, because it's all about forces, they're all intertwined. And with Newton's second law, our net force is equal to ma, because it's asking us all about the acceleration here. Now, Travis, let me draw a diagram here. Here's our, let's go over here. Here's our canoe. All right, here's Travis. I know what you're thinking. This guy's got to be an artist. Not really. Here's the dock. All right. Now, Travis pushes off the canoe, puts a force on the canoe. Now, here's what happens, is that Newton's third law says that if you push, in this case, if Travis pushes the canoe with a force of 155 newtons to the left in my diagram, that the canoe will put a force on Travis of 155 newtons in the opposite direction, equal in magnitude. So the force on Travis will be our 155 newtons. We know his mass is 75 kilograms, and we want to know his acceleration. And so again, I'm going to, solve for A here. Divide by 75 on each side. And our acceleration, whoops, we're not looking at direction here, the magnitude of the acceleration. I take 155 and I divide it by 75, and I get 2.07 meters per second squared. All right, now I want to also find the magnitude of the canoe. Now, they experience the same force. Travis is experiencing this red force. That's the canoe pushing back on Travis because he pushed the canoe. And so again, I'm going to use the same formula where I have my F net equals MA. All right. And again, the force is equal in magnitude, opposite in direction, but we're just looking at the magnitude of our acceleration. The canoe is 30 kilograms in size, in mass, and we want to know our acceleration. Well, now this time, I'm going to divide by 30 on each side to get A by itself. And that means the canoe is accelerating at a rate, let's see, 155 divided by 30, 5.17 meters per second squared. So that means the canoe takes right off very, very quickly, and Travis doesn't go as quickly. So if he's not close enough to the dock, he's going to get wet. Or I got another example of when that can happen to you. Let's see here. There we go.
Hey, people! Welcome back to the show! Ew! All right, the next step in opening your pool is taking the cover off. Yeah, you gotta get the cover off if you're gonna swim in it, but you want to have fun doing it. All right, here's how you do it and have fun, baby. Ew! All right, gonna be there. Okay, taking the cover off my pool. We're taking the cover off my pool. Gonna be there. Ah, you ready to go, people? All right, here we go. And I bet you didn't even know. All right. And then we're up here nice and high. All right, here we go. Cover off the pool time.
All right, so, whoops, escape that. So there's an example of somebody not following Newton's third law. That ladder was much lighter than him, and so it accelerated much quicker than he did, and so he did not make it back to the pool. A little side note there, he was okay. I think he broke his neck. He is able to walk today, that guy. He's the guy who, he was Jackass before Jackass, that guy. All right, now on to a little bit of a tougher example. Same situation here, sort of. Is that example 2? We have a man, 80 kilograms, and a woman, 60 kilograms, are each on a skateboard at rest on a frictionless surface. All right. And after the woman pushes the man, she has a velocity of 3 meters per second after 1.5 seconds. Calculate the acceleration and the final velocity of the man. Actually, we're going to end up finding both. We already know one of them. Now, here's what we have. We have, let's see here. I'm going to draw again my diagrams. How artistic I am. There we go. There's a man. There's his skateboard right there. Here's a woman. There's her skateboard. Let's see here. Yeah, I'll give her some better hair. There we go. All right, so they push each other. Now, the woman moves to the right. She pushes off of him. But because she pushes him, he moves to the left. But again, because she pushes him to the left, which I'm going to call negative direction here, he, in turn, not even trying, exerts a force back on her, which is equal in magnitude, but again, opposite in direction. Now, in this question, we know a lot of stuff about the woman. We know her final velocity. We know her time. We know her mass. So there's a lot of things we can figure out about the woman. So I'm just going to write those down. We got 2 different people here, but we'll go with the woman first. We know a lot about her. Okay, now, again, the first thing I know about it is her mass, is 60 kilograms. We know her initial velocity. right? They're both at rest. We actually know both of their velocities. So VI is 0. VF is 3 meters per second, standard units. That's good. And the time that this push is going on for is 1.5 seconds. So that's how long they're in contact for. Do I know anything else? I don't. All right. Now, what we do want to know is the acceleration of both the man and the woman. Well, we're going to find the man, but we're going to have to find the woman first because we know more about her. All right. So again, F net for our woman here is equal to MA. Now, I do know the mass of the woman, but I don't know the acceleration of the woman, because if I find the net force on the woman, then that's the same as the net force on the man. And so I'll be able to find the acceleration of him. Now, check out these variables we got here, specifically these ones here. Now, using our motion equation, one of our motion equations, I can actually find the acceleration of this woman. Because I've got A is equal to, this is our first equation of our motion equations, VF, minus VI, all right, divided by T. And so I substitute in my values where I have my acceleration. Again, I'm going to say right is positive because of my diagram, but again, we're just looking for the magnitudes here. Let's see here. So VF is 3 minus 0. Divided by 1.5. That is simply going to be 3 divided by 1.5, which is just 2 meters per second squared. Now, I can actually find, because of that, I have her acceleration. I can find the net force that the man applied to her because of Newton's law, because of the result that she applied it to him. He's the reaction force. All right. So I've got F net equal, her mass was 60 kilograms. So we'll put a 60 in there. Her acceleration is 2. Well, that makes calculating easy. And so F net is equal to 120 newtons. And again, this, because she pushed him, this is the reaction force where his body pushed back on her because of her action force. So that's our reaction force there. Now, again, getting back to the original question here. What's his acceleration and final velocity? Oops. Well, I can go down here and now I've got the man. Nice titles. All right, let's see here. So his mass again was 80 kilograms. All right, now I know the net force on him is equal to 120 newtons because she pushed him. That's the action force. All right. So again, using Newton's second law, I'm going to have F net or F equals MA. All right, my force is 120 newtons. His mass was 80. And find his acceleration. Well, again, I'm going to divide both sides by 80. All right, and see, they divide each other out. A is going to be equal to 120 divided by 80. Now, I'm assuming, and it should happen, it's going to be lower than 2 meters per second squared because she's smaller than he is. All right, and let's see here. I do 120 divided by 80, and I get 1.5 meters per second squared. All right, now that's his acceleration, slower than hers again because he's heavier and they're experiencing the same force. Now we also want to use the final velocity of the man. Well, I know how long they're in contact for. I know his initial velocity because they were both at rest. I now know his acceleration, so I can find his final velocity using the same formula. So basically, I'm just working in reverse here. All right, and so again, I have A is equal to VF minus VI all over our T or delta T, same thing. Again, his acceleration is 1.5. equals VF. That's what we're trying to figure out here. Minus 0 and divided by 1.5. All right, now let's see here. VF minus 0. Well, VF minus 0 is just going to be VF. So I'm just going to get rid of that. There we go. Because it's nothing. All right, now I've got a number equaling a fraction. Been here before, done this before. I'm going to create a fraction equaling a fraction. Again, so I can cross multiply. And so I'm going to have 1 times VF. Well, that's just going to be a VF. And then I got 1.5 times 1.5. And his final velocity is going to be, after 1.5 seconds, it's going to be slower than hers, right? Because she accelerated faster. She was 3 meters per second. 1.5 times 1.5, lo and behold, it is 2.25 meters per second. And there we go. So that is Newton's third law. For every action force, which in this case would be the red arrow, there's a reaction force, whether he meant to or not.
I have a question.
Sure.
Can you just explain the reaction and action force?
Okay, so I'll go back to that last example. Just give me a second here.